What if I told you that some of the most brilliant innovations in aviation history turned out to be spectacular failures? Welcome to American Memories, where today we're exploring the fascinating world of airplane technologies that seemed revolutionary at first, but ultimately proved they couldn't stand the test of time. From ejector seats that launched pilots through the floor instead of the roof, to engines that literally ate themselves alive, the history of aviation is filled with ideas that looked genius on paper, but turned into engineering nightmares in real life. These weren't just minor setbacks. These were innovations that promised to revolutionize flight, attracted millions in investment, and then failed so dramatically that they became cautionary tales whispered about in aviation circles. So fasten your seatbelts as we count down 10 airplane innovations that seemed destined for greatness, but ultimately crashed and burned in the most spectacular ways imaginable. Starting our countdown at number 10, we have the Heinkel He 280's downward-firing ejection seat, and this innovation was supposed to solve a major problem for fighter pilots. In the early 1940s, ejecting upward through a fighter's canopy was dangerous and often impossible during certain flight conditions. German engineers had what they thought was a brilliant solution. Why not eject the pilot downward, away from the aircraft's structure entirely? The concept seemed logical. The pilot would drop safely below the aircraft, deploy a parachute, and avoid any collision with the plane's tail or wings. Test pilots were initially optimistic, and the system worked perfectly during ground tests. But when they tried it in actual flight conditions, the innovation revealed a fatal flaw that should have been obvious from the start. Ejecting downward meant pilots were fired directly into the ground if the aircraft was flying at low altitude. Even worse, the downward ejection often didn't provide enough separation from the aircraft before the parachute deployed, leading to pilots being struck by their own planes. After several test pilots were killed, this revolutionary safety system was abandoned faster than a burning aircraft. The innovation that was supposed to save lives became more dangerous than staying with a damaged plane. At number 9, we encounter the Convair B-58 Hustler's escape capsule system, and this was supposed to be the ultimate in pilot protection technology. Instead of simple ejection seats, the B-58 featured individual escape pods that completely enclosed each crew member. These capsules were pressurized, air-conditioned, and designed to protect occupants from supersonic wind blast, extreme altitude, and even water landings. On paper, it was brilliant. A complete life support system that could keep pilots alive in any emergency situation. The capsules underwent extensive testing and seemed to solve every problem associated with high-speed, high-altitude ejection. Military officials were so impressed they considered making escape capsules standard equipment on all future aircraft. But reality proved much harsher than the test results suggested. The escape capsules were incredibly heavy, reducing the aircraft's performance and payload capacity. They were also mechanically complex, requiring constant maintenance and frequent repairs. Most critically, the capsules often malfunctioned during actual emergencies. Several pilots died when their escape pods failed to separate from the aircraft or tumbled uncontrollably after ejection. The innovation that promised ultimate safety became a death trap, and escape capsules were quietly retired in favor of traditional ejection seats. Coming in at number 8 is the turboprop innovation that promised to combine the best of propellers and jet engines, the Allison T40 compound engine. This mechanical marvel featured two turbine engines driving a single propeller through a complex gearbox system. The concept was revolutionary: provide jet-like power with propeller efficiency, creating the perfect power plant for large aircraft. The T40 generated incredible power, over 5,000 horsepower from a single propeller, and early tests suggested it would revolutionize both military and civilian aviation. Aircraft manufacturers lined up to use this wonder engine, and several major aircraft programs were built around its promised capabilities. The innovation seemed destined to dominate the skies for decades, but the T40 had a catastrophic weakness that became apparent only after extensive use. The complex gearbox system that combined power from two separate turbines was prone to catastrophic failure. When the gearbox broke, which it did regularly, it didn't just stop the propeller, it often exploded, sending metal fragments through the aircraft's wing and fuselage. Multiple aircraft were lost when T-40 engines literally tore themselves apart in flight. The innovation that promised reliability became synonymous with sudden, violent mechanical failure, and the T-40 was abandoned as quickly as the industry had embraced it. Number 7 brings us to one of the most embarrassing failures in aviation history, the McDonnell XF-85 Goblin Parasite fighter. This innovation was born from a genuinely clever idea. Long-range bombers needed fighter escort, but conventional fighters didn't have the range to accompany bombers on extended missions. The solution seemed obvious: create tiny fighters that could be carried inside bombers and launched when needed. The XF-85 Goblin was incredibly small, essentially a jet engine with wings and a pilot squeezed around it. The aircraft could be stored in a bomber's bomb bay, launched when enemy fighters approached, engage in combat, and then return to dock with the mothership. Military planners were excited about the possibilities: bomber formations that carried their own fighter protection wherever they went. But the Goblin's first test flights revealed fundamental problems that should have been anticipated. The tiny aircraft was nearly impossible to control in the turbulent air around a large bomber. Pilots couldn't maintain stable flight long enough to dock with the mothership, and several near-fatal accidents occurred when Goblins collided with their carrier aircraft. Even worse, the aircraft was too small to carry effective weapons or sufficient fuel for meaningful combat. The innovation that promised to solve bomber escort problems created new problems that were far more dangerous than the original challenge. At number 6, we encounter the rotating cylinder engine technology that promised to revolutionize aircraft power. The Wankel rotary engine adapted for aviation use. This innovation eliminated the heavy pistons, connecting rods, and crankshafts of conventional engines, replacing them with a single rotating cylinder that was lighter, smoother, and more reliable than traditional designs. Early aviation applications of Wankel engines seemed incredibly promising. They produced more power per pound than conventional engines, ran smoother with less vibration, and had fewer moving parts to brake or maintain. Several aircraft manufacturers began developing planes around rotary engines, and pilots praised their smooth operation and impressive power-to-weight ratios. But the Wankel engine's aviation career was cut short by a problem that became apparent only after extended use. The rotating seals that made the engine work gradually wore away, causing dramatic power loss and eventual engine failure. Unlike automotive applications where engines could be easily serviced, aircraft engines needed to be absolutely reliable for extended periods. Rotary engines in aircraft began failing at alarming rates, often without warning, leading to multiple forced landings and several fatal accidents. The innovation that promised smooth, reliable power became synonymous with unexpected engine failure, and aviation Wankel applications disappeared almost overnight. Number 5 introduces us to one of the most ambitious failures in aviation history: the pneumatic flight control system used on early fly-by-wire aircraft. Instead of traditional mechanical linkages or hydraulic systems, these aircraft used compressed air to operate control surfaces. The innovation promised lighter weight, faster response, and elimination of hydraulic fluid leaks that plagued conventional systems. Engineers were convinced pneumatic controls represented the future of aircraft design. The systems responded instantly to pilot inputs, weighed significantly less than hydraulic alternatives, and seemed to offer perfect reliability. Test flights confirmed that pneumatic controls provided exceptional aircraft handling and performance improvements that excited both pilots and engineers. But pneumatic flight controls had a fatal weakness that manifested only during extended operations. Unlike hydraulic systems that could maintain pressure indefinitely, pneumatic systems gradually leaked air pressure over time. As pressure dropped, control authority decreased, leaving pilots with aircraft that became increasingly difficult to control during long flights. Several accidents occurred when pneumatic systems failed completely, leaving pilots with uncontrollable aircraft. The innovation that promised improved reliability became less dependable than the mechanical systems it was designed to replace, and pneumatic flight controls were abandoned in favor of more robust hydraulic systems. At number 4, we have the boundary layer ingestion engine design that was supposed to revolutionize aircraft efficiency. This innovation involved mounting engines so they would ingest the slow-moving air in the aircraft's boundary layer, theoretically improving overall propulsive efficiency by accelerating air that was already being dragged along by the aircraft. The concept was brilliant in theory. Instead of wasting energy dragging air along the fuselage, aircraft could use that air for propulsion. Wind tunnel tests and computer simulations suggested significant fuel savings and performance improvements. Several experimental aircraft were built around this concept, and early results seemed to confirm the theoretical advantages. But boundary layer ingestion engines suffered from a fundamental problem that proved impossible to solve. The air entering these engines was turbulent, uneven, and filled with debris from the aircraft's surface. This irregular airflow caused severe engine vibration, rapid wear of internal components, and frequent compressor stall conditions that could destroy engines in minutes. Multiple test aircraft were lost when boundary layer ingestion engines failed catastrophically, and the innovation that promised improved efficiency became synonymous with engine destruction. Coming in at number 3 is the water injection system that was supposed to dramatically increase engine power for takeoff. This innovation involved injecting water into jet engines during critical phases of flight, cooling the combustion process and allowing engines to produce significantly more thrust without damage. The concept seemed perfect for aircraft operating from short runways or carrying heavy loads. Water injection systems worked exactly as advertised during initial testing. Engines equipped with these systems could produce 20 to 30% more thrust during takeoff, allowing aircraft to carry heavier loads or operate from shorter runways. Airlines were excited about the operational flexibility, and military applications seemed limitless. But water injection systems revealed critical weaknesses during regular operations. The water had to be absolutely pure to prevent engine damage, but maintaining water purity in operational conditions proved nearly impossible. Contaminated water caused severe engine corrosion and internal damage. Even worse, if the water injection system failed during a critical takeoff with maximum load, aircraft often couldn't maintain flight with normal engine power. Several accidents occurred when pilots couldn't abort takeoff after water injection failure, and the innovation that promised increased safety margins became a source of additional risk. Number 2 brings us to one of aviation's most spectacular mechanical failures: the contra-rotating propeller systems that promised maximum efficiency and power. These innovations used 2 propellers spinning in opposite directions on the same engine, theoretically eliminating torque effects and extracting maximum energy from the engine's power output. Contra-rotating propellers seemed to solve multiple problems simultaneously. They eliminated the need for large vertical tail surfaces to counter propeller torque, extracted more thrust from available engine power, and provided superior aircraft handling characteristics. Test flights confirmed that contra-rotating propellers delivered everything they promised: more thrust, better control, and improved efficiency. But these complex systems had mechanical vulnerabilities that became apparent only after extensive use. The intricate gearboxes required to drive 2 propellers in opposite directions were prone to catastrophic failure. When contra-rotating propeller systems failed, they didn't just stop working, they often destroyed themselves violently, sending propeller fragments through aircraft structures and sometimes into passenger cabins. Multiple aircraft were lost when contra-rotating propeller systems failed catastrophically, and the innovation that promised maximum efficiency became synonymous with sudden, violent, mechanical destruction. Finally, at number 1, we have the most catastrophic innovation failure in aviation history: the early jet engine afterburner systems that were supposed to provide unlimited power increases. These systems injected raw fuel directly into the hot exhaust stream, igniting it to produce massive thrust increases for short periods. The concept seemed perfect for military aircraft that needed maximum performance during combat. Early afterburner systems produced incredible thrust increases, often doubling an engine's power output, and gave aircraft performance capabilities that seemed impossible with conventional engines. Test pilots reported phenomenal acceleration and climb rates that revolutionized combat tactics and aircraft design philosophy. But first-generation afterburner systems had a terrifying weakness that became apparent only after they entered widespread service. The intense heat and vibration from afterburner operation often caused catastrophic engine failure without warning. Engines equipped with afterburners would literally melt themselves from the inside out, often taking the entire aircraft with them. The failure mode was so sudden and violent that pilots had no opportunity to react or escape. Multiple aircraft were lost when afterburner-equipped engines destroyed themselves in flight. and the innovation that promised unlimited power became a death sentence for pilots who used it. Early afterburner systems were hastily removed from service, and it took years of engineering development to create afterburner technology that wouldn't destroy the engines it was designed to enhance. So there you have it. 10 airplane innovations that seemed brilliant in concept but proved disastrous in practice. From ejection seats that fired pilots into the ground to engines that ate themselves alive, these technologies represent some of the most expensive and dangerous failures in aviation history. What's truly sobering is that most of these innovations were developed by brilliant engineers using the best available knowledge and technology of their time. These weren't amateur mistakes or obvious oversights. They were sophisticated solutions to real problems that revealed fatal flaws only after extensive development and testing. The aviation industry learned hard lessons from each of these failures. Modern aircraft benefit from decades of accumulated knowledge about what works and what doesn't, often paid for with the careers and sometimes lives of test pilots and engineers who discovered these limitations the hard way. These failed innovations remind us that progress in aviation isn't just about successful breakthroughs, it's also about learning from spectacular failures and ensuring they never happen again. Every modern safety system and design principle exists because someone, somewhere, learned a painful lesson about what doesn't work. What do you think? Have you heard of any other aviation innovations that seem promising but turned into disasters? Are there any modern aircraft technologies that make you nervous about their long-term reliability? Let me know in the comments below. I'm always fascinated by stories of engineering ambition that exceeded the limits of available technology. If you enjoyed this cautionary journey through aviation's greatest failures, make sure to hit that subscribe button and ring the notification bell so you never miss our explorations into the fascinating world of American memories. Until next time, remember that sometimes the most important lessons come from the innovations that didn't stand the test of time.